Ever wondered how steep your car is climbing? What if your car could tell you just how steep the road really is? Introducing a smart way to track pitch and roll anytime, anywhere. This DIY digital inclinometer gives real-time pitch and roll data right on your dashboard. Whether you're climbing steep hills or navigating uneven terrain, this device gives you live angle feedback, just like a high-end vehicle. Built with an ESP32 and MPU6050, it's precise, compact, and ready for adventure. A single press will calibrate it instantly. So stay tuned. This compact module is smarter than it looks. Let's go behind the build. At the heart of this project is the Lolin32 development board, based on the powerful ESP32 chip. It offers built-in Wi-Fi and Bluetooth, making it ideal for smart sensor-based applications like this one. The board features 30 pins, including multiple GPIOs, I2C, SPI, and ADC inputs. We'll be using GPIO 21 and 22 for I2C communication with the MPU6050 sensor and OLED display. For the display, we are using a 1.3-inch OLED screen with a crisp 128 by 64 resolution. It communicates over I2C, needing just two wires, SDA and SL, to work with our ESP32 board. The MPU6050 is a 6-axis motion tracking sensor combining a 3-axis gyroscope and a 3-axis accelerometer. It provides precise angle data for pitch and roll, which we use to calculate the car's inclination in real time. Here's a quick look at the wiring connecting the Lolin32 board with the OLED display. MPU6050 sensor using I2C and GPIO pins. So, let's connect the components together. Install Lolin32 OLED display and MPU6050 sensor on the breadboard as shown here. Before installing in the enclosure, it is always good to take trial on the breadboard. Both our OLED display and MPU6050 sensor runs on the 3.3 volt. So connect 3.3 volt pin of the Lolin32 board to the VCC pin of the OLED display. Now extend VCC pin connection to VCC pin of the MPU6050 sensor. Now connect ground pin of the Lolin32 board to the ground pin of the OLED display. Extend ground pin connection of OLED display to MPU6050 ground pin. So both our components will get power from Lolin32 board. Now take jumper wire and connect SDL pin of the Lolin32 board to the SDA pin of the OLED display. Now connect SDA pin of the OLED display to the SDA pin of the MPU6050 sensor. Now take another jumper wire and connect SCL pin of the Lolin32 board to the SCL pin of the OLED display. Now connect SCL pin of the OLED display to the SCL pin of the MPU6050 sensor. And now we are ready to upload the sketch. So let's open the Arduino IDE and understand the code of this digital inclinometer. Our digital car inclinometer includes smart features like pitch-based icon rotation, calibration, a visual roll gauge, and stable readings through averaging. It's designed for both accuracy and aesthetics, combining real-time motion with clean visuals and calibration support. We begin by including essential libraries for I2C communication, motion sensing, and OLED display control. We define the OLED display's dimensions and I2C address to initialize communication with the screen. A digital pin is defined for connecting the calibration button, allowing manual sensor zeroing. These variables handle raw acceleration data and calculate pitch and roll angles, which are crucial for determining the car's tilt. It also includes calibration offsets and averaging buffers to smooth out readings, along with dimensions for the rotating car icon bitmap. You can generate this image array from Image to CPP website. This section lists all the function prototypes used later in the sketch for better code structure and readability. The setup function begins by initializing the serial monitor, followed by starting the I2C communication. It then initializes the OLED and MPU6050 sensor along with the messages to display on the OLED screen. MPU6050 sensitivity is set to ± 8G with a 21 Hz filter for smoother readings. And then message to display to show sensor is ready. The loop function continuously checks if the calibration button is pressed, and if so, it initiates the calibration process. It then reads accelerometer data from the MPU6050 sensor and calculates pitch and roll angles using trigonometric formulas. These values are adjusted based on previously stored calibration offsets. To ensure smoother output, pitch and roll values are added to an averaging buffer, and the sample index is updated cyclically. The averaged values are printed to the serial monitor for monitoring, and the display is refreshed using the display car inclinometer function to visually reflect the current orientation. A small delay ensures the display and sensor readings remain stable and readable. After calibration, the average pitch and roll values are stored as offsets to zero out the sensor readings. The averaging buffer is reset to ensure clean values post-calibration. Then, a message is displayed on the OLED confirming calibration with the calculated offsets. The getAveragePitch and getAverageRoll functions return smooth angle values using the buffer. The drawRotated bitmap function handles rotation and rendering of the car icon based on pitch, ensuring correct placement on the display. The drawRoll gauge visually represents roll angle on a horizontal gauge with ticks and an indicator bar. Finally, display car inclinometer pulls all the elements together. First, it fetches the averaged pitch and roll values. The display is cleared for fresh rendering. The car icon is drawn at the top and rotated according to the pitch angle. Below the icon, pitch value is displayed with a degree symbol. A horizontal roll gauge is drawn below to give a visual representation of the roll. Finally, the OLED display is updated to show all elements together. And with this, we are ready to upload the sketch. Select the board from the board manager and port number and hit upload button and wait for the sketch upload to the board. Let's start by calibrating the modules. Here, I'm shorting the calibration pin to ground. The display shows a message asking to keep the surface level. It now takes a few readings to calculate the average pitch and roll. And just like that, the calibration is complete. We are ready to go. The module is powered by a compact LiPo battery, and you can conveniently charge it by connecting a USB cable to the bottom, perfect for in-car use without any clutter. Since my 3D printer was out of commission, I went old school and built a clean prototype enclosure using white cardboard. The rough dimensions of this enclosure are 60 mm by 50 mm by 30 mm. The OLED display can be hot glued securely to the enclosure. A dedicated slot carved out for the MPU6050 sensor. On the right, we have provided the space for the Lolin32 board, and a tactile push button for on-the-fly calibration is planned to install in the opposite direction to help with leveling inside the car. A small bubble level can be installed on top to calibrate the module in the car. This enclosure keeps everything compact and organized, and honestly, it can be made even smaller. For clean power and I2C wiring, I made custom vehicles to keep things tidy. So here it is, how each component will be placed inside the enclosure. As I said, I hot-glued OLED display for this prototype. Lolin32 board will go like this, keeping battery port on the back side and USB cable slot at the bottom side. Initially, I installed square yellow button for calibration, but I accidentally broke it, so I went with red one. The prototype has a sleek, minimal look, clean white finish with all components neatly tucked in. The OLED display pops out clearly on the front, giving it a modern dashboard feel. With the sensor slot, side-mounted button, and compact layout, it almost looks like a production-ready unit. And that tiny bubble level can be added on the top. A simple touch that adds both functionality and charm. This compact inclinometer is a real game changer for off-road enthusiasts and daily drivers alike. It gives you real-time pitch and roll data, helping you understand your car's tilt on steep slopes or uneven roads, something even many high-end vehicles don't show you clearly. Whether you're climbing hilly terrain or navigating a muddy track, this device can help prevent rollover risks by keeping you informed visually. Thanks to the onboard calibration button and optional bubble level, you can zero it perfectly for your car, making every reading precise and trustworthy. In future versions, we can integrate a Bluetooth module to meter live pitch roll data on a smartphone app. Adding a GPS module can unlock incline mapping and altitude logging. We can also include vibration alerts or audible beeps when unsafe tilt angles are reached, making it even more helpful on the road. And of course, with a custom 3D printed case, the module can look even more refined and dashboard integrated. Now that the module is ready, it's time to see it in action. And trust me, the demo reveals just how accurate and useful this compact setup really is. Watch closely as we simulate real-world pitch and roll scenarios. You won't believe how responsive and precise this little device can be. For anyone who loves off-roading or drives in hilly terrain, this tiny module could become your go-to angle tracker. A device like this can really help avoid risky tilts during steep climbs or side slopes. Safety with style. This compact inclinometer could actually alert you to unsafe pitch or roll angles while driving. Functional and futuristic. In the next upgrade, we are adding access point mode, so you can customize screen layouts, switch car icons, set buzzer alerts, and even upload your own graphics, all through a stunning portable web portal. If you want to see this upgraded version in action, along with a real-life test demo, don't forget to like, share, and subscribe to our channel. Drop your thoughts in the comments. Your feedback helps shape the next innovations. Let's build smarter together. Till then, I am DHK Dude, signing off.